All right, so today we're going to begin learning about kinematics. This is going to be very basic introductory information. We will begin to learn some vocabulary that is specific to physics in the upcoming lessons. But for right now, we're really just kind of classifying some basic vocabulary that we are going to be hearing throughout the course that will be very important for us to understand so that we can interpret questions and answers and other vocabulary definitions appropriately. Okay, so right now we are actually focusing on the first couple of words here on the screen, scalars and vectors. But before we get to that, I have a really important word for you. Magnitude is a word that you are going to see in questions and instructions and labs throughout the course. Now, the word magnitude is just a word that means value or number. Magnitude is not a variable. We do not measure magnitude. We do not calculate magnitude. We can calculate the magnitude of a variable. We can measure a variable, but magnitude all by itself is a word that just means number. So, in the example below, what is the magnitude of the car's speed? Notice that my answer says the speed is 5 meters per second, not the magnitude is, because we are not calculating, we're calculating the magnitude, but the word magnitude is not my unknown variable. Speed is what I'm really asking you for. Okay, I could have just said, what is the car's speed? And it would have been the same question. So the word magnitude is not the variable that I'm looking for. This is just telling you that I'm asking you to give me that numerical value for the speed of the car. Calculate the magnitude of force applied to the box. Again, force is what I'm actually asking you for. Now, we're going to continue to use this word magnitude, hear the word magnitude immediately in the definitions that we're going to cover today, but definitely throughout the course in questions similar to what you see here as examples. So it's very important that you understand what the word magnitude is and that you know that it is not a variable. Okay. So scalar and vector are two classifications of quantities that we are going to be basically categorizing our variables into throughout the semester. If you can understand the difference between scalar and vector, then if I tell you that this particular vocabulary word is a scalar value, that should clarify for you what the meaning of that variable is, how you would go about performing calculations for that particular variable. It should also clarify for you how that answer can be expressed. There's lots of different things that we can benefit, lots of different ways that we can benefit from just simply knowing the meaning of scalar and the meaning of vector. So scalar is a value that's just a number. So when I say speed is 5 meters per second, when I say the distance is 10 miles, when I say that the time is 30 seconds, those are all scalar values. They only have a number. Now, obviously, this number is followed by a unit. That's so we know what unit we're in, but it only has a number. So, okay, so then what other way is there to express a value than to have a number? Well, a vector is going to be a quantity that has a number, it has a magnitude, but it also has a direction. So for a vector, we have the numerical value and we have a direction. So when we're talking about certain vocabulary words, certain variables in this class, some of them will never have a direction. Take time, for example. There is no direction for time. Time is not up or down. Time is not right or left. Time is not forward or backwards. Time is just time. It is always scalar. But when we're talking about something like my velocity, this can have a direction. Now, I understand I have not taught you speed or velocity yet, and so we'll get into the details, but I just need to give you some examples, okay? So when we say that I am driving 20 miles per hour north, the 20 miles per hour is the magnitude of my velocity, and the north is the direction. You can see in the example here, I have 8 meters per second north, and then here I have a negative 9.8 meters per second squared. So in the first example, the word north gave me the direction. But where is direction in the second example? Well, 9.8 meters per second squared is the magnitude of my acceleration. In this case, that negative is there to give me information about the direction. So when we learn these vocabulary words, we'll come back and we'll revisit exactly what the details that I've just discussed means. But for now, I need you to know that scalar is just a number, okay? Vector is obviously going to be a number because this is a quantity, but it also includes direction. So that is your identifying piece of information there. Vectors have a direction. So this means that we can draw vectors by using arrows. Arrows are going to obviously give me a direction. So this side of the arrow is going to point in the direction. But where does the magnitude come from? Well, the magnitude is going to be represented by the length of the arrow. So for example, if I have a, let's just talk about velocity since we've already used that. If I have a velocity of 5 meters per second east, and then I have a velocity of 15 meters per second east. Well, both of these are going to be pointed to the east, but they are not going to be the same length. 5 meters per second is obviously a lesser value than 15. So in general, it should be a shorter line. It has a lesser magnitude. Now, I would really love for you to make it proportionally accurate, draw it to scale, however, whatever phrase you prefer to use there. But it's clear that 15 is 3 times larger than 5. So if this is my length that I'm going to use to represent 5 meters per second, then I'm going to do my best to make my length of my 15 meter per second east vector about 3 times as long. Now, how nitpicky am I going to be? Does it really matter? Well, yes, it matters. And how nitpicky I'm going to be is going to kind of depend on what I am grading, okay? I will tell you that if you are using vectors in order to create an illustration that you are then going to analyze, pull information off of, and then produce a calculation from the information that you took off of your own drawing, if you do not draw these vectors proportionally, if you do not draw it so that a larger magnitude has a longer value or longer length for its arrow, then your picture may come out to give you the wrong shape. So when you go to pull the information off of it, you're going to be pulling inaccurate data because your image is incorrect, your vector diagram is incorrect, and so you're just setting yourself up for a miscalculation. When we start talking about forces, you are going to be asked to create drawings using vectors. You are using arrows. You are going to create vector diagrams. When I look at your drawing, if you give me 2 arrows that are the same length, I am going to assume you want me to interpret them as being the same value. And if that's not the case, then that would be a wrong answer. And so, yes, it does matter. So please do your best to at least attempt to make them relatively proportional. Okay, this is not an art class, and we're not going to be pulling rulers out for every vector that we're going to draw. But I mean, when I eyeball your vectors, they should visually represent the magnitudes correctly. So like I said, vectors can be represented mathematically with numbers. So we're going to assign positive and negatives to specific directions. As a general rule, if we are talking about motion to the left, that will be a negative number. If we're talking about motion to the right, that will be a positive number. Now, in our class, when you say up, I am going to assume that you mean physically upward towards the sky. And when you say down, I'm going to assume that you mean physically down towards the ground. Because we deal with so many variables and concepts that have directions as part of their quantity, as part of their value, then we have to make sure that we are using these words appropriately, and those directions are going to affect our math work, because we will either be using a positive 5 in our calculation or a negative 5 in our calculation, depending on the direction. Okay, so I would like to point something out that hopefully makes this really easy to remember what direction is positive and what direction is negative. If I am in math class and I'm looking at a graph, if I were to write numbers on my graph, so 1, 2, 3, 4, so forth, -1, -2, -3, this would be 1, 2, 3, 4, and then here I'm running out of room, -1, -2, -3. You get the idea, okay? If I look at the types of values I have, the numbers here going in this direction to the right on my graph, those are positive numbers. So what did we say? To the right is going to be positive, just like the type of numbers we would see on a graph for that section of the graph. Now, if we are looking at the left side of the graph, these would be negative numbers. And we said that when we're going to the left, those are going to be negative values as a rule for our vector directions. So this is going to be the negative direction, because that is the type of values that we would typically see on a graph in math class. So now the directions hopefully make sense. So we can go a little quicker here. Up will be the positive direction. Down will be the negative direction. You will be expected to know what direction is positive and what direction is negative, and it will absolutely make a difference in your math work. All right, so since we're saying that we can do math with our vectors, let's just look at how that would go about. We'll continue using the example of driving, okay? So if I'm driving 20, let's say that these are distances. That'll make it a little easier. So let's say that I drive 20 miles to the right or to the east, and then I drive an additional 5 miles to the east. Well, to the east would be in the positive direction. So I have a positive 20 plus a positive 5. That's going to give me a positive 25. This means that when I take these two vector segments and I connect them, or I put them together, then they collectively combine for this magnitude to the right. So I can visually represent what is happening by drawing my arrows so that they are connected, and I can mathematically demonstrate or calculate what is happening by simply taking a positive 20 plus a positive 5. That gives me a positive 25. So a numerical answer of a positive 25 would tell me that my displacement was 25 meters to the right. Okay, now in the next example, they're going in opposite directions. So you might instinctively think to yourself, oh, I will subtract them. Yes, basically that's what we're doing. But I like to keep our instructions as generic as possible. I do my best to give you instructions or rules or formats that are going to work all the time. If that is ever possible, I will give you directions that work all the time. So I'm going to tell you that you are going to add your vectors together. We've already reviewed that vectors can be represented with positive and negative numbers to indicate their direction. So in this second example, my first vector is pointing to the west. So that is going to be in the negative direction. My second vector is pointed to the east, so that will be in the positive direction. So I am adding a negative 20 plus 5. So that's going to give me a negative 15 as my answer of this vector addition problem. Now, Ms. Espinosa, could I just say 20 minus 5? I mean, isn't that the same thing? Is it? I mean, if I say 20 minus 5, then is that going to give me a negative 15? Nope. It's going to give me 15, but it's going to give me a positive. And remember, we are dealing with quantities where the direction is part of its meaning. So a negative 15 means to the west. A positive 15 means to the right. So let's take a moment and let's look at how my vectors combine. And it looks like there's some crowding here of my picture from me uploading this. So let me just block this out for a minute so it's not in our way. So here I have my first vector, which is the negative 20 meters, right? So I drew this arrow in black first, and that arrow is pointing to the left or to the west. When I took my 5-meter vector and I combined it with my negative 20, I lined them up so that the point of the first arrow is where the line for the second arrow begins. And if I look at this first example, I did the same thing. The point of the first vector is where the line of the second vector began. And so we call this the nose to tail rule, okay? This means that we're going to take the nose or the pointy end of the arrow, and that's going to be the starting point for the subsequent arrow, okay? So I'm always going to connect them nose to tail. So that means that my resulting vector, my outcome when I have combined these two vectors, you can see here that they overlap. So this part of my vector gets canceled out. Now, if we think of somebody physically walking, I walked to the left 20 steps and then I backtracked to the right 5. So I'm now 15 steps away from where I started, right? My resultant is going to be from where the very first vector started to where the last vector ended. So here is the line segment of my vector, so that's going to represent my magnitude. And then what direction should it be pointed? Well, if we're looking at our vectors, it is that black negative 20 line that is the longer line, and that was pointed to the west. So my overall result here is that I am now 15 meters to the west of where I started. Mathematically, we have a negative 15, which would represent left or to the west as well. In this next example, they're both in the negative direction, so I would draw this nose to tail once again. So I'm going to choose to draw this black vector first, and so that has a magnitude of 10 to the west. And then I have the blue vector next, so the tip or the nose of my first vector is where the line of the next vector begins. So from here, I'm going to draw the line for my blue vector, and it is also pointed to the left. So the overall result of this vector addition is a length this long, which would represent 20 miles if we're doing our driving example, okay? It is to the west, and so that's why the math came out to be negative. In this last example, positive 20 plus negative 20 equals 0. Those lines are equal in magnitude but opposite in direction, so you can see when I line them up together, they perfectly overlap and completely cancel each other out. What if my lines are not along the same axis? So all of these examples, my lines were horizontal. If I were to turn these vectors so that they were vertical, everything would work exactly the same way. So if I made them vertical vectors, I would still connect them nose to tail, and it would still tell me the direction of my resultant. Okay, so the difference here is that these are either combining horizontal lines or we are combining vertical lines. Either way, my vectors are in the same plane or working along the same axis. When we move to the next slide, they are no longer working along the same line. They are now perpendicular to each other. So this would be a case where one of my vectors would be in the vertical axis, and one of my vectors would be in the horizontal. Oh, you can't see that because it's black. Let's pick a different color. One of my vectors would be in the horizontal axis, so they are perpendicular to each other. My resultant, my overall outcome, remember I said it's where we started for the first vector, and it's where the last vector ended. So this is my segment for my resultant vector, and it will have a direction, and that direction in this case would be pointed right here. Why? Because I went from here to this corner. That is the direction. And we'll talk about how that should be drawn in more detail in the future in class. I'm calculating using Pythagorean theorem, where A and B are my sides and C is the hypotenuse, and you will be asked to do some calculations using this Pythagorean theorem formula as well. Here are some examples for you. I'm not going to take the time to go through them at this moment. I am simply going to remind you that over here, I'm showing you that we are taking what our calculator gave us, and we are rounding this number according to the appropriate number of significant figures based off of the values I used in my calculation. So both of these have 2 sig figs, so 1, 2 sig figs. That 8 stays the same, so 18. Of course, if we were working an actual problem, we would have units with this, but 18 would be my final answer. Please remember to always round for sig figs with all of your calculations.